everyone, welcome to Tutorial 6. So to recap what we've learned so far today, we spent the past few tutorials discussing large-scale atmospheric, oceanic, and terrestrial processes that influence Earth's climate. And some of these include Hadley circulation, deep ocean currents, and the migration of the ITCZ, just to name a few. But before we spent time thinking about these large-scale processes, we started out the day learning about Earth's energy budget and the role of incoming solar radiation and the greenhouse effect on Earth's climate. We learned that incoming solar radiation is a primary control on long-term climate variability on Earth. But there are some other long-term climate forcings that are really important to discuss. Over the next few tutorials, we'll explore some of these long-term forcings in further detail. And to start out, we'll focus on the orbital cycles and the influence of forcing on Earth's climate. The orbital cycles are driven by three main components. These include eccentricity, obliquity, and precession. So eccentricity describes the shape of Earth's orbit. And you can see in this diagram that it can vary from being more elliptical to less elliptical. And this shape of Earth's orbit varies on a timescale of about 100,000 years. The second component of the orbital cycles is obliquity, and this describes the tilt of Earth's axis. So shown in pink, you can see that the Earth's axis can vary in its angle, and it can range from about 22.1 degrees to 24.5 degrees. And this variation in the tilt of Earth's axis occurs on a timescale of about 41,000 years. And the final component of the orbital cycles are precession. And precession describes the wobble of Earth's axis, and this varies on a timescale of about 21,000 years. These three components affect Earth's position relative to the Sun, and therefore they affect the amount of incoming solar radiation that reaches Earth. And if you recall from Tutorial 2, we discussed the importance of incoming solar radiation to Earth's climate. So overall, the collective effects of changes in eccentricity, obliquity, and precession are strong drivers of Earth's long-term climate and are responsible for triggering the beginning and end of glaciation periods. Glacial periods, or ice ages, are long periods of reduced global temperature that result in an expansion of ice sheets. Interglacial periods are times of increased global temperature and a retreat of ice sheets. For example, these maps are showing the extent of Northern Hemisphere ice sheets over North America and Europe during the most recent glacial period, which occurred about 21,000 years ago. And these glacial interglacial periods are driven by changes in incoming solar insolation that vary in response to changes in the orbital cycles. So let's take a closer look at this and the relationship between the orbital cycles, insolation, and glacial periods. In this figure, the yellow curve is showing changes in insolation over the past 1 million years. The blue curve is showing changes in eccentricity, the green curve is showing changes in obliquity, and the red curve is showing changes in precession. And this yellow insolation curve is essentially the sum of all of these forcings of the orbital cycle. If you look closely at the variations in the insolation, you can see that there's shorter timescale variations in response to precession and obliquity, as well as some longer-term trends and patterns in the insolation that reflect changes in eccentricity. And this black curve on the bottom is a record of glaciation. And the actual data that is represented by this curve is a measurement known as the delta 18O, or the oxygen isotope ratio. And we'll learn more about this later this week, but for now, it's just important to know that this measurement represents changes in temperature, and this reflects the differences between the glacial and interglacial temperatures. Similar to the orbital cycles and changes in insolation, this record of glaciation also varies in a cyclic pattern. And if we look closer, we can see that periods where it's hot and interglacial correspond to instances of increased insolation, whereas periods where it's cold and a glacial period correspond to instances in which solar forcing is decreased. This figure in the upper left is the same glacial stage figure that we saw in black on the previous slide. And again, just showing changes in the oxygen isotope ratio, which records changes in temperature. So this figure is showing a relatively long time period of 1 million years. So it's difficult to see more recent changes on such a long time period. We can zoom in and just focus on this last glacial to interglacial period that occurred over the past 22,000 years. Now we're looking at temperature change over the past 22,000 years. And you'll notice that over this time period, there's a warming of about 6 to 8 degrees Celsius. So looking at temperature change on this time range, the past about 700 years of temperature may seem relatively stable, and actually even spanning back to about 2 to 6,000 years, we don't see that much of a temperature change. However, if we zoom in even further, we start to see a different story. Now we're looking at temperature change over the past 2,000 years. Looking at this record, we see some short-term annual variability in temperature, but overall, there's a relatively constant long-term temperature until the past couple of hundred years, where we start to see a rapid increase in temperature. To examine this a bit further, we can zoom in once more to just look at the historical temperature since 1880. Looking at this record, we can very clearly see that the rate and magnitude of warming has increased over this time. So over the period of about 100 years, global temperatures have increased by about 1 degree Celsius and are continuing to rise. And comparing this recent warming on Earth to past temperature change on longer timescales, such as we've looked on the previous slide and on this slide, can help us to identify natural versus anthropogenic climate variability. And in the context of natural temperature variability over the past hundreds of thousands of years, the rate of recent and future temperature change is unprecedented and poses threats to our planet. So comparing historical temperature change to temperature variations during past climate states can provide context for present-day warming. Recent and future temperature change is often presented as an anomaly relative to a past climate state or historical period, and this anomaly represents the change in temperature over this time period. Later in this course, we'll learn more about how interpreting current climate change in the context of natural climate variability much further in the past is also helpful for predicting and adapting to future climate changes. But for now, we'll focus on recent temperature change over the past 20 years. In this tutorial, we'll learn how to use X-ray to compute and plot the global temperature anomaly over the past 20 years.